Jeremy throws a ball into the air. The height in meters of the ball after t seconds can be modelled by the function h of t is equal to negative 0.15 t squared plus 2.1 t plus 2.25. Now that we have a function that models the real world scenario, we can answer different questions about it. So part A asks us, at what height does the ball leave Jeremy's hand? And we know the ball leaves his hand when the time is 0. So we can find the height when the time is 0, h of 0, is equal to negative 0.15 times 0 squared plus 2.1 times 0 plus 2.25. Now we know anything times 0 is just 0, so we get the height when the time is equal to 0 is 2.25. Therefore, that is the height in meters at which the ball leaves his hand. Part B asks for how long the ball is over a height of 6 meters. So for this one, we need to firstly find out at what times is the height of the ball 6 meters, and then solve the inequality for when is it greater than 6. So we want to find out when is negative 0.15 t squared plus 2.1 t plus 2.25 equal to 6. So if we subtract 6 off both sides, we get negative 0.15 t squared plus 2.1 t minus 3.75 equals 0. And now if we divide everything by negative 0.15, so divide all of the left-hand side by negative 0.15 and the right-hand side by negative 0.15, we find that the equation is equivalent to t squared minus 14t plus 25. And of course the right-hand side is still 0. And if you try and inspect that to find the factors, you'll find it very, very difficult. So we're going to use the quadratic formula. So we know that t is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And for this equation, we know that a is equal to 1, b is equal to negative 14, and c is equal to positive 25. So with that in mind, we have t is equal to negative 14 plus or minus the square root of b squared, which is negative 14 squared minus 4 times 1 times 25, all divided by 2 times 1. And now I'll let you go and do all the simplification on that, but you'll find that the values we get out are t is equal to 7 minus 2 root 6 and 7 plus 2 root 6. So now that we've done that, we need to interpret what this means. So we'll do a quick graph of h of t. So here we have the height and the time, and our function will look a little bit like this. So we know that the height is 6, is at this point here, and that we have just found these two coordinates, here and here. So if we want to find the total time that the ball is above 6 meters, we can simply do t2, if we let that one be t2 and this be t1, t2 subtract t1. So t2 take t1 is equal to 7 plus 2 root 6 minus 7 minus 2 root 6, and that will give 4 root 6. And that's roughly 9.80 seconds. Next up, we're asked how long does it take for the ball to reach the maximum height, and what the height of the ball is at the maximum point. So to do this, we can either complete the square or use the axis of symmetry, because the maximum height is going to fall at the vertex or the turning point of a parabola. So in this video, we're going to use the axis of symmetry, which for this will be t is equal to minus b on 2a. And our values of a and b come from this formula up here. So we have A is equal to negative 0.15, B is equal to 2.1, and C, not that we need it for this, but that is equal to 2.25. So plugging that in, we get that T is equal to minus B, which is 2.1, over 2 times negative 0.15, and that gives negative 2.1 over negative 0.3, which gives positive 7 overall. And you might recognise that number from the 7 minus 2 root 6 and 7 plus 2 root 6 from part B. So now that we have that, we simply need to plug 7 in as the time, because that's the time, the answer to part C, that the ball reaches its maximum. So for part D, we just need to find the height at the time of 7. So we're going to have negative 0.15 times 7 squared plus 2.1 times 7 plus 2.25. And that, if you use a calculator or you go through the mental arithmetic, you'll get that that is equal to 9.6. So we have, how long does it take for the ball to reach its maximum height? It takes 7 seconds. And for part D, the height that the maximum reaches is 9.6 meters. In part E, we want to know at what time does the ball land on the ground after Jeremy's thrown it. So the ground is defined as a height of 0. So what we want to do is work out when does this function 0.15t squared plus 2.1t plus 2.25 equals 0. So if we divide both sides by the negative 0.15, this will just help to simplify the equation we're trying to solve. So we'll get positive t squared minus 14t minus 15 equals still 0. So this is a quadratic that we can easily inspect to find the factors. So we put t here, and that'll expand to give the t squared. And next we need to look at the factors of negative 15 that add together to give negative 14. So if we use negative 15 times by positive 1, we know that that will give the negative 15, and when we add those together we get the negative 14t. So using the null factor law, we say t minus 15 could equal 0, or t plus 1 could equal 0. So if I add 15 to both sides of this equation, we get t is equal to 15. And if I subtract 1 from both sides of this, I get t is equal to negative 1. However, and this is important for practical domains, we know that time is greater than or equal to 0. Therefore, only one of these solutions is possible, and we have t equals 15 is when the ball will next hit the ground, which means in 15 seconds after it's released from Jeremy's hand. So lastly, part F gets us to graph this function over a suitable domain. So we've found a lot of the key points on here. We know that the ball leaves Jeremy's hand when the time is 0 and the height is 2.25 meters. So that's the y-intercept, or the h-intercept in this case. We next knew that the ball came up and reached a maximum height after 7 seconds, and that was a height of 9.6 meters. Lastly, we know that the ball comes down and it touches the ground after 15 seconds, which is a height of 0. So if we put a parabola shape through these, that is our function graphed over a suitable domain. So getting the computer to just graph this a little bit nicer for me, that is the graph of h of t over a suitable domain, and these are the answers that we've gone through. So part A asks us at what height did it leave Jeremy's hand, which was 2.25 meters. We knew the ball spent around 9.8 seconds above 6 meters. We know that it reached a maximum of 9.6 meters after 7 seconds of flight, and that maximum was at 9.6 meters high. We also found that the ball reached the ground after 15 seconds of time travelling through the air. And for part F, if you refer to this graph, that's the functions over a suitable domain.